I'd like to welcome everyone to the 2022 version of ORAC's annual Fall Forum. My name is Paul Wrigley, and I'm ORAC's Managing Director, for those that don't know me. We do have some guest speakers lined up for today, talking on a variety of topics, varying from the seriously educational to the hilariously funny. We have a Guinness World Book record holder with us today. He'll be showing us how to remember names, faces, and facts, which is a skill I would certainly like to develop. I have trouble remembering my own name some days. We'll also be recognizing some of our loyal ORAC members with awards for the years of support. And for the first time, we will be presenting the first awards to students who applied to our new scholarship program. They'll be joining us a little later. Before we begin today's sessions, I'd like to thank the associate members who have generously supported us with their sponsorships of this event. Special thanks goes to our gold event sponsor, Yorkland Controls. Thanks to Gavin Barrett and Jerry Salucci. We'd also like to thank our silver event sponsors, who are Carrier Enterprise. Thanks to Brett Freeman. Keep Right Refrigeration. Thanks to Trevor Woods, who I saw a few minutes ago. Kilmer Environmental, thanks to Glenn Kilmer and Ed Carney. Armstrong Fluid Technology, thanks to Paul Scarafile. And Office Central, thanks to Adam Miller. All three of those guys I just mentioned have tables over there, so feel free to visit them during the events today. Thank you once again for helping us to make this event a success. Now, our first speaker today, to kick off things, we have Andre Harry from Armstrong Fluid Technologies, who will be presenting the fundamentals of variable speed pumping systems.
My name is Andre Harry, Armstrong Fluid Technology. I've been with Armstrong a combined 20 years. I started with them, I left, and then I came back in 2008. So in the industry, in the pumping industry for over 31 years. I know I don't look it. See, you said add some humor, okay? That's my kick at that. But anyway, what I'd like to talk today about is variable speed pumping. And I know it sounds very entertaining, but it's something that's dear to my heart. And through that, I've got a bit of an agenda. First of all, getting an understanding of what ASHRAE 90.1 is and its application. Then a review of the affinity laws. You know, we're going back to second year mechanical engineering for those people who remember that. Review of how variable pumping works, and then we're going to understand an understanding of the different methods of control. One of the reasons that this is very, the importance of this is that we have a traditional control strategy, and back in around 2006, Armstrong Fluid Technology purchased a company in the UK, Holgram and Brooks. And at that time, they were developing or integrating a technology that was able to control a variable speed pump without the requirement of a differential pressure switch. And that was unique. Now, we come to today, and Armstrong has advanced the technology, and some of our competitors have also brought that to the marketplace as well. Grundfos, Xylem, Taco. So we're all in the same form. But what I find a lot of times is that there's not an understanding of how this works. So we're going to cover that. But when we talk about pumps, and I was talking to a colleague here, in our industry, we typically look at a pump as a minor component in the bid and spec market or in the design build. You have your chillers, you have your towers, and then you have your pumps. So price-wise, they're not major. But what we've got to understand is the pump is the integral piece of equipment in that system. And when we're talking about HVAC. So in plumbing, pumps move water. In fire pump applications, pumps move water. In HVAC, Pumps move energy. Water is the medium. And the way a pump works and understanding how variable flow works is key to some of the solutions that we're bringing to the marketplace today. We're talking about decarbonization, we're talking about sustainability, we're talking about electrification, and we're talking about efficiency. So we know that with electrification, we're generally going to start moving to heat pump technology. And with that, understanding how we're moving that thermal mass with a pump is going to be critical to the efficiencies of those systems. And if you look at even today without heat pumps, what are some of the struggles with chilled water plants? Delta T control, which is moving that thermal mass fluid. My joke with my daughter's dating a young man that works for one of you contractors, and I won't name which one, but God bless him, because he's the only guy I can talk to at dinner about this, but we always laugh. How many times has he gone to a site with a condensing boiler that isn't condensing? Why? Flow. So understanding flow is key to that. So anyway, with that being said, traditionally in our industry, we've always sized pumps based on a constant speed, constant volume mentality. So it's designed for that peak load demand. 90% of the time, demand is within 20% to 80%. So using variable flow is critical to the efficiencies of systems. ASHRAE 90.1 was created or developed around, I think it was 2003, 2007. Started around 2000. But it's an energy standard for building design for everything except for low-rise. So here in Canada, we use NECB 2015, and it's harmonized with ASHRAE 90.1, the 2013 version. And it provides a minimum requirement for energy-efficient design of buildings. In the US, 49 of the states apply at least a minimum of the 2004 version of it, and some of the progressive ones will go up to the 2016. California uses Tier 24 and Part 6. There's a 2019 version available now, but that hasn't been applied to our building codes as of yet. What I'm focusing on today is that energy legislation that applies to the pumping side. And if you look at it, what it's saying is that individual chilled water pumps serving variable flow systems having motors exceeding 2 horsepower shall have controls and or devices that will result in pump motor demand of no more than 30% of design wattage at 50% of design flow. Okay? So, and if you look at it, when it first came out in 2007, that applied to a 50 horsepower pump. Today, at 2016, it's down to 2 horsepower. So here in Canada, we're still at 2013 standards, so it's a 5 horsepower. And 2019 is coming out now. So where did ASHRAE come up with this? First of all, what are they saying is that we shall have a control that when we reduce the flow of the system to 50%, we are using 30% of the energy. Valves, two-way valves, reduce the flow to that fan coil. We're going to use 30% of the energy. How did they come up with that? Well, that's where second-year fluid dynamics comes into play. It's the affinity laws. And the key there being that if you look at the affinity laws, which govern how every piece of rotating equipment pumps work, you drop the speed, the power consumed drops by the cube to the squared. It's as simple as that. So understanding that all ASHRAE has done is applied the affinity laws to real-world applications. That's number one. But number two is, and this is the key here, is understanding the difference between a pump curve and a control curve. So pump curve, control curve, system curve. And it's really, oops. Your pump curve is based on the speed the pump is operating, okay? Your system curve always goes from 0, no flow, no head, and moves up exponentially. So as there's more resistance, as you're moving more water through your piping network, the resistance increases by the square. The control curve is the line that a pump is operating on in a variable speed application. And the way the control curve is determined is based on your DP sensor location. And what they're saying then is that in our systems, when we go to 50%, we're operating here, we should be using 30% of the power. Challenge is, in a traditional system, to get that control curve. So if we look at our traditional systems today, we basically have a pump, a drive, and a differential pressure switch. So it's a PID loop technology. Basically, you have that DP sensor, which is it's a diaphragm with 2 ports on either side. And when a valve closes, the pressure changes from one side to the other, you deviate from your set point. When you deviate from your set point, that DP sensor sends a signal back to your drive to either speed the pump up or slow it down. Drive, pump don't know anything other than to get back to their set point. And once they get back to that set point, you're back to your steady state. You're now at your new flow demand. Struggle is then DP sensor location. So ASHRAE has mandated that if we're using a differential pressure switch, that DP sensor is located at the most hydraulically remote load in the system. You're putting it out there as far as possible. Simple for the mechanical contractor is to locate that differential pressure switch in the mechanical room over between the supply and return on the pump side. And a lot of engineers will specify 2/3 of the rundown. So if you look, mechanical room, 2/3, ideal location. That DP sensor's location will dictate what the control curve looks like. So when you have that DP sensor located in the mechanical room where we see a lot of installations because it's easier, basically you require the head pressure at design and at minimum flow to be almost identical, because you've got to put pressure on this side and you have to have that pump running all the way over to have pressure on that side. What that does is you have a relatively flat control curve operating now, and there isn't significant deviation in power consumption on your system. So, stopping right here, in simple building retrofits, without doing anything other than walking in and relocating that differential pressure switch, we have an opportunity of reducing pump control or pump energy by anywhere from 20 to 25% in buildings that have those sensors in the mechanical room. When we have that DP sensor at the hydraulically most remote load, what that means then is that, all we need to do is have that minimum head pressure to get that volume of water to the sensor or the load, and then we have our control curve. And as a result, we're able to optimize the pumping situation or the solution, and we meet ASHRAE standards. Now, one of the challenges in this, first of all, is that once a DP sensor is located in the system, it's fixed. It's very difficult to move. And there could be times, depending on the complexity of the system, you may have the DP sensor at the most hydraulically remote load, but your pump will not then generate the head required at some low load situations. Which would result in fan coils located closest to the mechanical room being starved. So engineers then will specify 2/3 of the run, and that's where they're trying to balance out the requirements for ASHRAE while still making sure that they're covering that scenario. So, where are we today? Well, one of the big things about Armstrong is we've moved to an integrated solutions approach, and I think a lot of you have seen our design envelope pumps with the controller and the pump and the motor as one integrated solution in the market. What we've done then, basically, is something that we refer to as sensorless control. Now, giving a bit of step back on how this works. The motors that we use in all of our centrifugal pump applications are referred to as variable torque motors. And what that means is that the torque that the motor is going to generate is dependent on the load the shaft sees. So, and what that then happens is that if there is no load on the shaft, there is not going to be a significant amount of amp draw. As resistance on that shaft increases, the amp draw required to overcome that resistance increases as well. So it varies, the torque varies with the load it sees on the shaft. If the load on the shaft is greater than what the motor can produce, you overload the motor. That's a variable torque motor. In our industry, what do we have at the end of the shaft? An impeller. And that impeller is creating pressure to move water through the system. As valves open or close, the pressure required either increases or decreases, and the amount of work the motor is doing is either going to increase or decrease. It varies the torque, varies the load. That's the affinity laws. So now, historically, if we look at a traditional system, if I have a pump operating at this point right here, and a valve starts closing, I'll start moving up the speed line. If I have a differential pressure switch, it will see an offset on the pressure and adjust the speed accordingly to get back to the control curve, back to a stable situation. With sensorless control, when I'm operating at this point and a valve starts closing, my work or my brake horsepower starts to change. And the end result is that I see a change in the amount of work I'm doing, and I adjust accordingly to get back to the control curve. That's the concept or the technology behind it. So how's it done? First of all, what we're doing is we're monitoring the speed and the power the pump is operating at, and then adjusting accordingly when that changes as valves open or close and loads change in the system. What we do, and what everybody does, is this is a mapped performance. So now what we're doing is that we are taking that pump, we put it on a test rig, and we run it through a series of speeds. And at those different speeds, we plot the power to head at that speed and the power to flow at that speed. So if you're looking at that, we've created a matrix of data. Now, when we're operating, if we know if the system changes, we can adjust accordingly. So what this looks like actually is it's a data set. That's all. So we run it at different speeds, we plot power, we plot head, and we plot flow. Once we have that data, we then define what the control curve looks like, which is Bernoulli's equation. Basically, we tell the system, this is our design point at peak demand, and this is what we need at minimum system pressure or at zero flow. With this point and that point, we then create the control curve. And now the pump, based on monitoring the speed and power, knows where to operate at any given time. And that's the technology that's embedded in sensorless pump control. But the beauty of this then is as I said before, once you have your DP sensor located in a system, or if you have a complex system with multiple differential pressure switches, it's a challenge to control or to adjust if there's something wrong. With this technology now, we are able to continuously define the control curve. Sorry, where am I? So we can run off of the quadratic. We can run at constant flow or at constant pressure. When we commission, if we've never seen an engineer oversize a pump, but when we commission, if the pump is oversized, we can fixate on the flow required, and the pump can reset itself to that design point as well. So commissioning becomes a lot more simplistic. We've run into situations where an example would be Toronto Housing had a building where they had multiple risers. And they had cold spots within that building. So originally they were running off of sensorless and they had that control curve. Well, because of the multiple risers, we had to increase the head required. And so we moved from a quadratic to more of a flat line. Now, we're not meeting ASHRAE 90.1, but we're solving a comfort issue in that building because of the way the system has been set up. So the point here being is that there's this distinct advantage in terms of this technology being applied correctly, but it's understanding how it works is the first key to that. Now, the other big thing is, and as we move forward, is the pump now acts as a flow meter. And that's the next step in terms of the technology now, is that you have flow as an output from your hydraulic device without the requirement of putting a flow meter in. And people will ask, well, how accurate is the flow meter? It's within 3 to 5% of accuracy based on the flow meter that we have in the factory that's calibrating this data at the beginning. So now, with that data, in more complex systems, especially on chiller sides or boiler applications, instead of controlling based on a set point, we can actually send a flow demand back to the device to provide the flow required to the system without looking at operating off of a pressure signal. So that's where the technology comes into play. So, that kind of summarizes what I wanted to talk about today. But hopefully it gives you an idea of where we're moving in terms of what variable speed pumping is all about. And it's not just simply a device that's in the building. And with that being said, I always bring this up. So you just remember, load is equal to flow times delta T. Our pumps are moving thermal energy. Understanding how those pumps operate with the system, optimizing it, we're able to optimize the pump energy required to move that thermal load, but we're also able to optimize the performance of the building, moving that thermal from one potential to another. And that's all I have to say today. So, any questions?
Your flow, would engineers accept that as an alternative flow meters in the system?
Yes. So, case in point, one of the larger projects we did recently was our organogram, which is a marijuana grow ops out in New Brunswick. And this is really unique technology because they have heating chillers, and then they have 3-barrel heating and simultaneous heating and cooling chillers in this application. So 2 500-ton and 3 750-ton units in there. It's a variable primary, variable secondary, and we are using our flow signals to control the entire loop of the system. So, because we're doing simultaneous heating and cooling, and it actually, it has, we've provided the complete plant controls in there that we were talking about earlier. But what it's able to do then is, instead of looking at pressures, it's calculating that flow value. And the key here is now, if I know what my flow demand is in my secondary loop, instead of waiting for the primary loop to respond, I tell the primary, I need 800 GPM. Those pumps go to 800 GPM without hunting to get to that signal. But that's kind of some of the applications of the technology. So, that's it. Any others here?
Yeah, back to that project, were you saying that for the line, you got that,
You can do pumps on each riser. That's the equipment was all in there already. So they had multiple risers, and they already had, I think it was 3 20 horsepower pumps in a headered configuration. Short of trying to put everything in on each of the risers, which is another solution. Which it was adjusting the flow so that that minimum would be able to provide the flow required to all the risers in the system. Yeah, and that's the beauty of the technology. So, taking my Armstrong hat off, it's just understanding how to set up the controllers with what's available there. Yeah.
ultimately your load is determined by the T and wherever it is, right?
Yes.
So why don't you just go to the WT, just use that signal to control your flow as opposed to pressures or whatever.
No, so that's in a systems approach, and you're absolutely right. We can actually control on temperature as well, which is another application where we actually even incorporated our pumps with a geothermal loop. And so now with that, because of the technology that's available, we can do data acquisition as well. And we're monitoring the flow and the temperatures. And so in that scenario, first of all, geothermal is geosync. It's a thermal battery, and you want to maintain that temperature in that system so that you're not overheating or overcooling it. And what we're doing is we're monitoring that temperature and at the same time monitoring the building load temperatures as well so that we can harmonize the system. And that's where some of the technology comes into play there as well. So. Any other questions? Well, thanks for showing up early. You know, I don't have a comedy routine other than, you know, I love talking about pumps and HVAC, but look forward to, if you have any questions, I'll meet you at the bar after all of this is done. Thanks a lot, everybody.
That was a great entree. Thanks for that presentation, and it wasn't nearly as dry as I was expecting, so you had some questions. That's always a good sign. And as an appreciation of your showing up today and giving us that little speech, we appreciate it. Thanks very much.
Thank you very much.
Yeah,
Thank you.
you.